Hello, my name is Mike Brey, and I am the Director of Development for Oracle NoSQL. And today we're going to be discussing Oracle NoSQL Cloud SDK, developing with ease. So today we're going to be covering a little bit about the Oracle NoSQL architecture, the different data models that are present for Oracle NoSQL. We will talk about JSON, parent-child tables, and we will wrap up with talking about our SDKs and our IDEs. So Oracle NoSQL is a client-server shared nothing data store architected for HA from the beginning. Whether you are looking at it from the point of view of the cloud service or the on-premise product, it is essentially the same at the database level. The key difference between the two is the cloud service is fully managed and the on-premise product is self-managed. If we take a look at this diagram from the top down, you have the key space, and the keys are piped through a hash function. This key is commonly referred to as a shard key. The output of the hash function is the shard that the record will be stored in. In the example above, we show three different shards. Each shard is made up of replication nodes, or RNs for short, and those nodes will either be a leader node or a replica node. The light blue circles are the replica nodes, and the dark circle is the leader node. Write operations will always be sent to the elected leader, and read operations will go to the fastest replication node. And the system internally keeps track of the response times of each of the replication nodes, so we always know which one is the fastest. If the leader were to fail, we will elect a new leader, and this happens without any manual intervention and happens really seamlessly. We have the notion of fault containment zones, and that's really a physical concept. You want your RNs for a given shard to be on different hardware, whether this is at the network level, the disk level, the storage node level, what have you, and then that way you can protect your HA. And in our cloud service, we set it up this way. What is on the bottom of the screen is what we call the KB store, and it is physically made up of storage nodes, or SNs. A storage node is a physical or sometimes a virtual machine with its own local storage, and this is intended to be commodity hardware. It's useful, but it's not 100% required that all the storage nodes be identical from a hardware standpoint. And this just simply makes the management of them a little bit easier. And depending upon their capacity, a given storage node will host one or more replication nodes. And if more than one, those replication nodes will be from different shards. And this helps to protect the HA characteristics. For the cloud, we use bare metal dense IO shapes, and those use locally attached NVMe based SSDs. So now let's talk about the cloud architecture. And the same database sits in both the on-premise and the cloud. And for the cloud, we ensure full HA is provided. In the different OCI regions offered by Oracle, they are either backed by multiple availability domains or what we call fault domains. In this slide, we are showing multiple availability domains. Each shard in the database has a replication node in each of the availability domains, and this gives us 3 copies of the data. And as you can see, we have like 3 green tables, 3 red tables, 3 blue tables. If any of the availability domains goes down, the database can stay up and running. If 2 of them go down, the database can still stay up and running. And of course, if all 3 go down, it probably means that the OCI region was taken out by some kind of catastrophic event. And then not only is our service down, all the other services are going to be down as well. On the left-hand side of the screen, we see different interfaces into the cloud service. The top one shows a customer application that is built with the NoSQL SDK. We have SDKs in many different languages, and the beauty of these SDKs is they work equally well against the cloud service and against on-premise installs, whether those installs are clusters in your own environment or whether they are hardware installs in another cloud vendor. In fact, These same applications can, with small changes to the connect string, can access both of these environments. And we have customers that have chosen to store some of their application data locally and other parts of it in the cloud. The next one down shows the console, and we have a full functioning console interface where you can create and drop tables, you can insert, update, delete data, you can run queries against your data, and we are regularly adding enhancements to the console to make sure that the experience is even better for you as a user. Finally, at the bottom of the screen, we show the OCI SDKs, and there are many SDKs published in various languages that you can use for your application. These SDKs perform the operations over a REST interface. While they do not provide all the functionality of the NoSQL SDKs, they're very straightforward and simple to use and regularly used by our customers. On the right-hand side of the screen, we show our current OCI map. Presently, NoSQL is live in 33 regions throughout the world, and the number is constantly growing. On the left-hand side, we show the different languages that are available for the NoSQL SDKs. We have SDKs in all the major languages. We have Java, Python, Node.js, Go, C#, and Spring, which is our framework. At the top of the screen, we show our scripting capability. You can do scripts in Terraform or the OCI CLI or the command line interface. And using a combination of the Oracle NoSQL service as well as other services offered through Oracle, such as the API gateway and functions, you can build very reliable serverless applications. Since we've been talking about the Oracle NoSQL Database Cloud Service, it is time to mention a few key points about the service. The service itself is fully managed, and what we offer is a table. In other words, you do not allocate OCPUs or CPUs or disks or memory or a database, you allocate a table. And with this table, you must define the reads and the writes and the storage requirements. We have different pricing models available, so you can pick the pricing model that best works for you. Our development team has been maniacally focused on performance since day one, approximately 12 years ago. Each release is exhaustively tested to ensure we are meeting our performance criteria. We have customers across a broad range of use cases such as personalization, metadata storage, IoT, and customer scale access. These use cases rely on the different characteristics that we offer: reliability, scalability, predictability, availability, and performance. And within the console, you can monitor your table's usage of reads, writes, and storage. And this information is readily available at your fingertips. Since we talked about provisioning, I thought it would be useful to take a look at some of the APIs that are involved that controls that. So you can dynamically increase or decrease your provision throughput. We have three things that you can control: your number of read units, your write units, and your gigabytes of storage. Here we're showing one of our APIs through our Java SDK. So we're doing a table request. So we do a set statement to create the table, fairly simple table here. Then we do a set table limits. That sets the table limits to 2,100 and 500. And then we set a timeout, and then finally we execute that, and then we get the results back in a table results object. Now, later on down the road, some other point in time in your application, you go, hey, I might be having a lull or having a low period. Then you can go ahead and reduce one of your provisioned units. In this case, we'll just reduce the read units down to 1,000. You use the exact same table request call. This time we don't need the set table statement, right? Because the table's already created. Presumably we've been using it for a while. So it's the exact same call, except just with the set table subclause. And then I do want to mention is that this is a DDL call from the perspective of NoSQL, and you can only perform 4 of those in a minute. Unlike our competitors, we offer 3 different data models, and you are free to choose which one works best for you. We offer key value, fixed schema, and schemaless. You can view fixed schema as a traditional way it is set up in a table in a relational database. You have columns, and each of those columns has an assigned data type. And if you try to store data in a row and the data type does not match, then typically you get an error. For schemaless, this is commonly referred to as document or document store or schema list or some variant of that. Different SQL vendors use different terminology. And this record is usually an auto-generated key and a JSON document. The beauty of a JSON document is the fields can change from document to document without having to make a DDL change to your table. And this is very robust for today's applications. Key value is basically a two-column table where one column is the key and the other column is the value. The type of value can range, but the common ones are either binary or JSON. And with this data model, we offer get and put APIs to access these records. And as you can see under each of the different columns, we show a sample of what the create table would look like. And then in the first two cases, we show an example of accessing the data. For the key value one, we show basically a get API. Actually, we're showing a put API. And then for the schemaless one, we're showing a query request API. So one of the really wonderful features of NoSQL is it doesn't matter which data model you choose because we have SQL interoperability. In this slide, we are showing the schemaless model on the left and the fixed schema on the right. With the schemaless model, we have a key called cookie ID, and we have a JSON document called content. Over on the fixed schema side, we have the same key called cookie ID, and then we took the JSON document and we mapped it over to a record data type. So if we ask the same question in both of these scenarios, find all visitors to my site in November who are males between 24 and 30 years of age, then what you'll see at the bottom of the screen is you will see the exact same SQL statement. The SQL statement is identical. Since we use dot notation to traverse the path, it's very straightforward to use in either of these schema environments. We have taken the hard work out of the development experience, and you don't have to think about, oh, if I'm using this data model, then I have to code it this way. Or if I'm using that data model, I have to code it differently. And regarding JSON, I wanted to make a general point. JSON objects are self-describing, and the schema information is carried along with the record. The schema information is repeated record by record by record. So if you have a situation where the size and the shape of the JSON object is fixed, then it's beneficial to consider using the fixed schema approach, and you avoid storing the overhead of the redundant schema information. We offer a rich set of secondary indexing with indexing on just about anything. We use standard JSON dot notation to access fields within a JSON document. It's very intuitive and simple to use. Looking at the create table statement at the top of the slide, we have a table with several different columns in it. We show an example of creating a simple scalar with the name index. We also show an example of creating an index on an array with the interest index. We also find it very common that composite indexes are needed in the industry, and we're showing that as well with the fname index, where we have two fields, the first name and the last name. And finally, you can create indexes into any data element within a JSON document. On the right-hand side, we see an exploded view of the contact details field. And down in there, highlighted in the red, we see the zip code. And so our final example is showing creating an index on the zip code field called zip index. And we just use the path notation to access it. And since the zip code is a atomic data type, it's a number, then we just do it as any atomic. When you think about the idea of real-world data, it's easy to find use cases where you have a list of objects, and each of those objects contains a list of objects. Let's take a look at such an example from the airline industry. In fact, a baggage tracking example. We have all flown from one destination to another, and many times we bring along with us more than one bag. And sometimes, our trip requires more than one flight leg along the way. So in this example, we have a passenger. This passenger has multiple bags. So we have an array of bags. And if we do multiple flight legs, then we have an array of flight legs. And every time we get to an airport, our bag has to get unloaded, has to get moved, has to get put on another aircraft. And all throughout that process, there's various RFID scans that happen on your bag. So as you can see, as the bag moves along, we're collecting a bunch of data, and it's very easy to see that we have a set of nested arrays or an array within an array within an array. And in this example, we're showing the strength of NoSQL, where you can create an index on an action deep within a nested array. So we're showing the create index statement on action airport. And again, since that's a string, it'll be any atomic. So it's an atomic data type. And we create that index deep within a series of nested arrays. At the bottom of the screen, we show an example query where we list the passengers who had bags handled at the Miami airport. So through this example, we would then go gather the data through the use of the index that we just created. So this extremely powerful index functionality comes into play when handling real-world data. Oracle NoSQL easily handles JSON data. This is a three-part example where we are showing a create table, inserting data into it, and then updating it. We are inserting one row. We're using a map value construct here. At the bottom of that, we're showing another put request. Here we're showing some data from an individual with a phone number. And the update statement is great because you can do a lot with it. There are 5 different things that you can do with the update statement, and we are showing you 2 of them here. You can do an add, you can do a set, you can do a put, you can do a remove, and you can do a set TTL, which is basically a time to live. And add will add new elements into an array. Set will update the values of one or more existing fields. Put will add new fields to a map or update existing ones. Remove will do exactly what the name implies. It will remove elements from either an array or a map. And finally, set TTL will update the expiration time. So you can have an individualized expiration time per row. With one SQL statement, you can perform all 5 of these functions or any combination of them. The beauty of the SQL statement is all the work happens on the server side, and it totally bypasses what a lot of other systems do, where they have to read the record, bring it to the client, modify it on the client, and then finally write it back to the server. And for those of you with a SQL background, the update statement acts pretty similarly to standard ANSI SQL, except we've enhanced it to work with the rich data models that NoSQL provides. As in the example above, there's a where clause, which must point to a single record in the table. A returning clause can be added to the statement, which will return the list of fields after they've been updated. And this can give you confirmation that the update happened as you expected it to. The clauses in the update statement are applied in the order that they appear, and the next clause will immediately have available to it the results of the prior clause. So in this example, the effects of the add statement is immediately available to the set clause. So again, this is very powerful tool that we have within our APIs. Next, we're going to talk about child tables, and the NoSQL table hierarchy is an ideal table model for applications that need some data normalization, but also require predictable low latency at scale. The hierarchy links different tables to enable left outer joins, combining rows from 2 or more tables based on related columns between them. Such joins execute efficiently since the rows of each of the tables are co-located in the same shard. Also, writes to multiple tables in the hierarchy obey transactional ACID property rules. And so within a single write, if you're writing to multiple tables, either all the writes will succeed or none of them will. In the child table, in addition to having a primary key defined, it inherits the primary key of its parent. This helps to tie the 2 of them together. You could say that the inherited keys are implicit. Now that we have discussed some of the details around child tables, let's take a look at the example. On the left-hand side of the screen, we show several different table create statements, and they represent going down the hierarchy, the left-hand side, or excuse me, the right-hand side of the hierarchy. And each table in the hierarchy is created separately, and the naming of the table is very important. The name of the child is established by walking the hierarchy from the parent using dot notation. Then if you do a show table on the parent, it will tell you that it's a table hierarchy, and it will give you a list of the tables that are in that particular hierarchy. Oracle NoSQL offers two kinds of join statements, the left outer join, which is illustrated above, and nested tables. We view the left outer join as a subset of nested tables. And with nested tables, you can perform joins either in the upward direction or the downward direction in the hierarchy, and you can even do both within the same statement. So this makes nested tables very useful, and it provides a lot of power at your fingertips. So let's move over to some of our SDKs. And here's an example from our Node.js SDK. And this is a sample function doing a create. And what we have on this table is we define our create DDL statement. And then we go through the table DDL API where we have to specify the DDL that we're going to use. And then we see the table limits. And in this particular case, we're using the mode of provisioned. And we covered the table limits and the provision model in prior slides. So in this case, we're doing 50 read units, 50 write units, and 25 gigabytes of storage. And then we set complete to true. And in our Node.js API, everything within Node is basically done asynchronously. So that's a trigger that basically, return the value of the table being active when we can do that. Then we set up the for completion API. So we're going to sit there and wait until the other one is completed. And then we can print out a couple of log messages saying that our table is completed and what its current state is. So here's another example. This is an example using select. So here we're going to create a statement. This is a little bit more of a complex statement where we have a declare. So we're going to declare a variable. Then we're going to have our select statement. And then we're going to select information out of our database using the variable $last name. So we're going to set up a rows variable, set up some other variables, count and res. And in this case, we're going to do a prepared statement. So we call the prepare API. We send it along the statement. And before we execute a prepared statement, because we have a variable in there, then we have to do the bindings to it. So we do a prepared statement.bindings, and that'll set up the bindings for us. And in this particular routine, we're going to pass in the last name. So we'll basically bind the last name to our variable that we have set up. And then we're going to put this in a loop. So we create a loop, we do a query, and on all of our queries, right, since we don't really know in advance how many rows are going to get returned on each and every select statement, we have this continuation character. So you set up your continuation character, you execute the query, a block of rows will come back. In this case, we're shoving those rows into the array, and then we check our continuation character. As long as it's not null, then we continue. We'll grab the next block of rows, and eventually we'll be done. And in this particular case, then we will return the rows. Here's another case. This case is a update statement. And in this update statement, we already talked about this several slides ago. Here we have a declare, again, a little bit more of a complex statement. We start out by taking the input that we got, and then we basically convert that string input into a JSON structure. Then we declare our statement with the update. And then notice on this update statement, we actually have a returning star. So that way we can verify the information that we updated, as well as what we did before. We're going to prepare the statement. We're going to do the bindings. We're going to do the variable bindings. In this case, if you take a look at the where clause, we have where ID equals $ID. So we're basically going to be updating a single row. We go ahead and we execute that query in the client.query statement, and then we return the row that got returned. And since we know that we only operated on one row, we're only going to return a single row in this particular instance. So let's move over to a couple of slides with some Python examples on them. Here we have a create table statement, very, very similar to what we saw in the node.js example. We have our statement, then we just do a print in there to print out the statement. Then we have a table request. Each of the languages have their own little nuances. So, sometimes the terminology that we use across the APIs is a little bit different for each one. We try to keep, the language and the terminology sort of native to the core language that we were using. Here we have a table request, then we have the set statement, then we have a set table limits. In this particular case, this table is getting created with 30, 10, and 1, 30 reads, 10 writes, and 1 gigabyte. And then we do a do table request to actually execute it. Down at the bottom of the slide, we're showing a table usage request. And where that's useful is, you could put this in a program at some point in time in the future. You may go, oh, I want to adjust my limits, right? But before you do that, you go, hey, what are they right now? So here's a API that you can use that you can go find out what your limits are currently set to. Another example in the Python SDK, we're showing putting some rows, we're showing a get request, and then we're doing a delete request, right? So the delete request will delete a row, get request will get the row, and then the put request will put rows. In this particular example right here, for the put, right, we put that into an array, right? So basically we set up the values we want for our table, we do the request set value, and then we do a put request. So this is going to operate, and basically within this loop, we're basically going to add 10 rows into our table. Again, all of these are very easy to use, fairly simple constructs. Finally, we show you, the top example is showing a multiple write request. The beauty of the multiple write request is you could stick multiple requests basically into an array, and then with the write multiple API, right, you can then go and have all of those trigger on the back end or on the server side. So it basically reduces the back and forth from the client to the server. So if you have a bunch of rows that you want to insert, this is a very powerful way to do that. And then finally, we wrap up this slide with showing you a prepare statement, and then basically executing that prepare statement, right? So we set that up, we prepare it, we execute it, and then we fire off the query. So really similar to what we saw in the Node.js examples. We have plugins for IntelliJ, Eclipse, and Visual Studios. All of our plugins, you can create tables, you can view tables, you can look at information about the tables, you can look at indexes, you can execute selects. And our whole idea here is to have a very easy development experience. You want to connect and go. And we want you to focus on the application development and not dealing with, how to do all the connection, what you connect to, and all that kind of stuff. Here's an example from the Eclipse plugin. We have the create table statement on the right. Down there at the bottom of that slide, you can see show DDL. So on the left-hand side, if you were to hit show DDL, it'll pop up a little box that shows you the DDL that you created. So, fairly easy to use to create the table, very, very intuitive. Here's an example using the Visual Studio. This is an example where we are inserting some test data. We insert the test data, in this case, using a JSON format. You can see the SQL down there in the blue. There's also the ability to come along and fetch data as well. And in summary, I want to say that, Oracle NoSQL runs anywhere you want. You can have it run on-prem, you can have it run in the Oracle OCI cloud, you can have it run in other vendors' clouds. We offer NoSQL, we offer our language SDKs in all of the popular languages that are available. We find that developers easily transition over to Oracle NoSQL because of its strong SQL base. You don't have to develop an understanding of some other language. Most folks really, come out of college these days learning SQL. It's easy to develop in your own with your favorite IDE. And we have a free tier available in the cloud that, if you want to do some basic development and get going, you can do that essentially at no cost. So I want to say thank you for listening to this presentation. I hope you got some new knowledge after listening to it. So have a great day.